In this video, we're going to be talking about the life cycle of a star. The life cycle of a star can vary based on the mass of the star and the astronomical factors that are present around the star. So first, we're going to be starting off with the nebula. The nebula is where the beginning of a star starts. The nebula is basically a humongous cloud of gas and dust that are brought together from the gravity at the center. Now, the way the sun forms is it happens through fragmentation. A small or large piece of this nebula slowly breaks away, and eventually this fragmented part of the nebula starts to gather all that dust and gas around it and starts to build up in size, eventually creating a protostar. So basically, the gravity at the center causes all the dust and gas to come more closer towards it, and eventually the temperature and pressure of this protostar starts to increase. It actually increases so much that hydrogen particles start to fuse together to become helium. This is called nuclear fusion. This fusion releases a large amount of energy, and by releasing this energy, eventually all the gas and dust that were at first being collected into this protostar are pushed away. It takes billions of years for hydrogen particles to fuse together and create helium. So now we're going to be moving to the main sequence star. So this can go into two different paths. One is an average star, and one is a massive star. So keep in mind that the average star lasts much more longer, or a smaller star lasts much more longer than a massive star. And I'll explain that. In an average star, what happens is when the hydrogen is fusing, it doesn't need that much energy for it to push against gravity. So the thing is that gravity is trying to push and collapse the star, and the fusion that's happening in the core of the star is pushing that gravity away. And because it's pushing that gravity away, it's creating a nice kind of ecosystem, or a stabilized ecosystem, where there's no power getting too big. And however, for a massive star, it needs a lot of fusion and a lot of energy to be able to push that gravity, because there's more gravity pushing on a massive star compared to an average star or a smaller star. Hence, massive stars do not last as long as average stars. So the main sequence of a star is basically the main part of its life. This is where most of the hydrogen fuses into helium, and what happens is it basically goes on with its life. It fuses, and throughout its gravity, it collects things like planets or other kinds of gases or asteroids, and then eventually, fast forward like a couple billion years, and slowly you have these stars starting to die. So now, if you're an average star, you're going to go through this path. But if you're a massive star, okay, you're going to go through this path. We're first going to start off with the average star. So in the average star, we have a red giant. Eventually, what happens is the average star starts to lose hydrogen. And when it loses hydrogen, it then has to fuse with other kinds of heavier elements like helium. And because this is a smaller star, it can't fuse that many elements at all. And because it can't fuse that many elements, slowly what happens is there's now a pressure difference. The gravity then starts to counteract with the hydrogen fusing out, and because there's not that much energy, it has to fuse helium. And by fusing helium, there's a humongous expansion. Because helium is a heavier element, and when you fuse helium into carbon atoms, for example, then what happens is it releases even more energy compared to the hydrogen fusion. And because of that, the red giant expands. If we look at our sun, located in our solar system, we're able to see that our sun is basically a typical average star. And because of that, eventually, after 5 billion years, the sun is going to expand into a red giant, because it's going to lose all its fuel for hydrogen fusion. Our sun is in the main sequence right now, but eventually it'll turn out to be a red giant. All right, now we're going to move to a white dwarf. So what happens is eventually the red giant burns up all of its helium to the core, and when it has no helium, then the gravitational pressure starts to build up on that red giant. When the gravitational pressure starts to build up on the red giant, eventually what happens is it completely shrinks the size of the star, making it to the size of Earth, or if it's a smaller star, it may be smaller than the Earth. But whatever it is, eventually turns into a white dwarf star. This white dwarf star doesn't release any heat, but it does release light. So for the next quadrillion years, we're going to see the white star slowly using up all of its light energy. And eventually what happens is when it loses all of its light, it completely turns into a black dwarf. This is the end of the star's life, and eventually, after like quadrillions of years, this star then gets recycled into the solar system back into dust, and eventually it'll turn into a nebula, where the star then begins again. And now we're going to move on from a massive star. So this is a much more exciting compared to this path because there's a lot of things happening here. But now we're going to be moving on. So the massive star, when it runs out of its hydrogen, it then fuses helium. And like the regular red giant from average star to red giant, it then expands from the helium fusing into carbon. When helium fuses into carbon, this causes a great amount of energy to be released. When this energy is released, what happens is instead of being like when we look at the average star and the red giant, the average star over here definitely grew in size. But for a massive star, we could also see that it grew in size. So this grows at a more exponential rate compared to the red giant. Red supergiant grows much more bigger than the red giant. Now, since the red supergiant needs to challenge gravity, meaning that since there's a lot of gravity now pulling on it, it needs to make up even more heavier elements to be able to counteract that gravity. And what happens is throughout the next couple 100 million to a billion years, it then fuses these heavier elements to be able to counteract gravity's gravitational pull against the red supergiant. So helium fuses to carbon, carbon fuses to oxygen, oxygen fuses to neon, and keep in mind these are heavier elements, and when we fuse these elements, it releases even more energy. So oxygen fuses to neon, neon fuses to magnesium, magnesium to silicon, silicon to iron. Now iron is so dense that it doesn't fuse, but it pulls all the materials inward by its own gravity. If the red supergiant is very big, as in the sense that it is able, it can just create like even more heavier elements, then it then turns into a supernova. So what happens is the supernova contains so much energy that the atoms, when they fuse together, like heavier atoms such as gold, silver, and uranium, these elements are very unstable. And because they're so unstable, there is so much energy that the star or the red supergiant collapses, creating a supernova. Now, fragments of these supernova are then returned back to nebulas. The only part that remains is the core, just like over here with the white dwarf. Everything else is returned back into outer space. So first we're going to be talking about a neutron star. Neutron star, after the explosion, is just the leftover material, or like the core, from this massive star. Now, the core is extremely dense since it was fusing a lot of these elements together, which are also very dense. So since it's extremely dense, if the core of this is less than 4 times the mass of the sun, then it turns into a neutron star. If it's 5 times more, it turns into a black hole. So a neutron star is made entirely of neutrons, as the name says. And if you don't know what neutrons are basically like neutrally charged particles, which means they have no charge, and since they have no electrical charge, they're really not doing anything in space. And after quadrillions of years, they later again get recycled into space. Now, for black hole, if it has 5 times the mass of the sun, so even more mass than the sun, then what happens is the core collapses on itself because it's so dense. Since it's so dense, not even light can escape from this area. The only way we're able to identify that a place is black hole is if it's pulling things together, because since it's so dense, it has an even greater gravity. And since it's not fusing anything, it's not growing in size, and it's not releasing anything. So what that means is now it's taking in everything around it so that it's able to fill in the space that the black hole has. So as of now, we're unsure what black holes do, and we have many possible theories. But as of now, we just know that black hole forms after a really massive star is too much dense that its core collapses on itself. They can be identified by the objects around it, like if it has a horizon zone, which is basically this like a bunch of dust and a lot of materials around it that shows how much the black hole is able to capture. So anything outside of that, you're kind of safe, but inside you're going to be sucked towards the black hole, and we're not sure what happens inside. Then another way we could also identify is through the radiation that leaks out from the edges of the black hole. This is the life cycle of a star.